So let's jump right in. There's a problem that's, well, it's literally overflowing our closets. I mean, we're talking about textile waste.
And the scale is just, it's immense.
It really is. Globally, we're generating over 92 million metric tons of this stuff every year,
And here in the U.S., it's around 17 million tons.
with a staggering two-thirds of that, 66%, going straight into a landfill. It's just this mountain of old clothes that it doesn't go away.
And it's not just a land problem, right? It's a
Yeah.
climate problem. When those natural fibers like cotton break down, they release really potent greenhouse gases.
Absolutely. Which is why today's deep dive is so timely. We're focusing on a brand new study, just published December 20th, 2025, that proposes a solution.
And it's not just about managing the waste.
No, it's about converting it into something actually useful. We're talking about sustainable and maybe even carbon-negative energy.
The technology they're proposing is small-scale, modular bioenergy with carbon capture, utilization, and storage. BECCS for short.
Okay, so let's unpack that. The mission for this deep dive is to look at 4 specific scenarios from this paper.
Right. They're comparing 2 main types of material, the feedstock.
One is 100% cotton. The other is a 50-50 blend of cotton and PET, which is that common plastic.
And for each of those, they modeled it with and without carbon capture technology.
So we're going to use a life cycle assessment, the LCA, to check the environmental side, and a Techno-Economic analysis, or TEA, to see if it makes any financial sense.
And the potential prize here, if we get this right, is huge. The biogenic part of this waste, so just the cotton and wool, globally, that represents an estimated 75 million metric tons of potential CO2 removal.
Wow.
So using this underutilized biowaste stream is, it could be crucial for hitting our net zero goals.
Okay, so let's start with the material itself, the feedstock. Textile waste is messy. It's never just one thing.
Exactly. It's usually a mix. About half is biomass, cotton, wool, and the other half is derived from fossil fuels like PET.
And that's why the researchers were so smart to model the 2 scenarios separately.
They had to. They needed to isolate the impact of that fossil plastic. So scenario 1 is 100% pure cotton. That's all biogenic carbon.
So when you capture that carbon, you're literally pulling CO2 out of the atmosphere.
You're vacuuming it up. But scenario 2, the 50-50 blend, that's different.
Right.
Capturing the carbon from the cotton part is removal, but capturing it from the PET is just mitigation. You're just stopping new fossil emissions from getting out.
And that distinction is really the core of this whole thing, isn't it?
It is. It's the beating heart of the entire study.
So are we building a real CO2 vacuum cleaner or just a slightly cleaner power plant? Let's talk about the facility they modeled. It's a very specific size.
It is. It's a modular, decentralized facility. It only processes 100 dry metric tons a day.
Which feels small.
It is small, and that's the point. Textile waste isn't like municipal garbage that all goes to one place. It's dispersed.
Right.
You can't justify a massive central plant for old T-shirts. You have to bring the solution to the waste.
That makes a lot of sense. So how does this little plant actually work?
The core is a process called combined heat and power. Basically, they burn the textile waste to create high-pressure steam.
Which turns a turbine, generates electricity.
Right. And then comes the critical part. The flue gas, the smoke from combustion, gets routed to the capture system.
Okay, and what's happening there chemically?
It's a pretty standard post-combustion capture process. The flue gas enters what's called an absorption column.
And it mixes with a chemical.
Exactly. A powerful amine-based solvent called monoethanolamine, or MEA. You can think of MEA as a kind of chemical magnet that just grabs the CO2 molecules and pulls them out of the exhaust.
So the MEA snags the carbon. Then what?
Then the CO2 is stripped back out of the MEA, it's compressed, and then it's ready to go.
And go means either buried deep underground for permanent storage.
Or utilized, turned into other products like fertilizer or methanol.
We should probably hang on to that MEA chemical for a second, because the study mentions that running this CCS system requires its own inputs.
That's a crucial point. It's not a closed loop. The solvent degrades over time.
So you have to keep topping it up.
You do. You need fresh MEA. You need sodium hydroxide, that's NaOHE, to help reclaim and clean the used solvent. And you need activated carbon to filter out impurities.
And all of those chemicals have their own environmental footprint from being manufactured.
Precisely. All of that adds embodied emissions and, of course, costs.
All right, let's get into the life cycle assessment then, the environmental scorecard. The first bit of news is really good, and it's clear.
A very clear win. All 4 of the waste-to-energy scenarios, even the ones without carbon capture, were way better than just landfilling this stuff.
Why is that?
Well, landfilling creates methane, which is a super potent greenhouse gas, plus you get all this toxic leachate polluting groundwater. Combustion is just fundamentally a cleaner option than that baseline.
Okay, so that's the good news. Now for the complicated part. We add this fancy carbon capture system to solve one problem, global warming, and the study shows it creates new ones.
Yes, this is where the trade-offs really come into focus.
What are they?
Okay, so while CCS absolutely crushes the global warming potential, it increases the burden on two other environmental metrics. First, the CCS scenarios showed a higher acidification potential.
Acid rain.
Basically, yeah. And it's directly linked to that MEA solvent we just talked about.
Hmm.
As it degrades, it releases ammonia, and that contributes to local acidification.
So we're trading a global benefit for a localized burden right around the plant. That's a tough trade.
It is. And the second one was higher ecotoxicity potential.
Which one comes from?
The upstream emissions. It's the pollution generated from making and transporting the MEA and all the other chemicals needed to keep the capture system running. You're essentially outsourcing the environmental damage to the chemical industry.
That definitely puts a big asterisk next to the clean energy label.
Yeah.
But let's look at the main event, achieving net negative emissions. This is where the pure cotton versus the blend really separates.
The difference is stark. Let's look at the 100% pure cotton with CCS. This system achieves an incredible net CO2 removal. We're talking negative 48,533 tons of CO2 equivalent per year.
And that's true removal because all the fuel is biogenic. Every bit of carbon you capture was recently in the atmosphere.
Exactly. The carbon removal efficiency is 91%. It is a genuine CO2 drawdown machine.
Fantastic. Now, what happens when we mix in the plastic, the 50-50 blend?
The performance drops off a cliff. The net CO2 removal is much lower, negative 22,523 tons per year.
Less than half.
And critically, because of the PET, the system is still emitting about 6 tons of new fossil fuel-based CO2 every single day.
So that plastic is just dragging the whole climate performance down.
It completely dilutes it. Half of what you're capturing is just cleaning up a fossil fuel mess you just made. So the overall carbon removal efficiency plummets to 59%.
So if your goal is actual rapid CO2 drawdown, the blend is just.
Yeah.
It's not the right tool for the job.
Not nearly as effective.
Okay, so we know the environment demands pure cotton. Let's see what the money says. Time to switch to the techno-economic analysis. And this is often where things get tricky.
And the study has a really a counterintuitive financial finding.
To understand it, we need two key metrics.
Right. First is the levelized cost of electricity, or LCOE. That's basically the price you need to sell your power at to break even. It's the affordable energy number.
And the second?
Is the levelized cost of CO2 removal, LCOR. That's the net cost to pull 1 ton of CO2 out of the air. That's your climate benefit price tag.
So LCOR tells you how much it costs to buy 1 unit of climate solution. Okay, so here's the finding that just makes you scratch your head.
Go on.
The 50-50 cotton PET blend, the one with the plastic, has the lowest LCOE. It makes the cheapest electricity at 17 cents per kilowatt hour.
And on the other hand, the best one for the climate, the 100% cotton with CCS, has the highest LCOE. It makes the most expensive power at 29 cents per kilowatt hour.
The whole thing is flipped on its head. Why? Why is the clean fuel making more expensive electricity?
It comes down to basic physics. The fossil-based PET has a much higher energy density than cotton.
It just burns hotter.
It does. So when you burn that 50-50 blend, you just generate more electricity for every ton of waste you feed in. That higher output drives down the levelized cost of electricity. The fossil fuel makes it a better power plant, financially speaking.
Okay, so the blend makes cheaper electricity.
Yeah.
But when we look at the other metric, the LCOR, the cost of the climate benefit, the story reverses.
Completely. For the pure 100% cotton system, the LCOR is $329 per ton of CO2 removed. That's in the ballpark of being competitive.
And the blend.
For the 50-50 blend, the LCOR skyrockets to $777 per ton.
More than double the cost for the climate benefit. Why is it so much more expensive?
It's because LCOR only rewards true atmospheric removal. Remember, with the blend, half the CO2 you're capturing is just from the fossil PET.
Right, that's mitigation, not removal.
Exactly. So you paid all the money to build and run the capture equipment for that CO2, but it doesn't count towards your removal benefit. It dilutes the efficiency and makes the actual climate benefit you achieve incredibly expensive.
It's like an economic penalty for not using pure biogenic waste. But of course, these costs can be offset. There are incentives, right?
Yep.
You can sell the CO2.
You absolutely have to. The viability of these systems depends on it. In the US, you have the Section 45Q tax credit, which is $85 a ton for stored CO2.
And if you sell it on the market.
The market price for liquid CO2 can be much higher, around $380 a ton on average. These revenue streams are non-negotiable if you want the 100% cotton system to even get close to breaking even.
Let's circle back to the size for a minute. We said this modular design is small, only 100 tons per day. How does that size affect the bottom line?
It's a huge factor. The small scale creates a high capital intensity problem.
Meaning it's expensive to build for its size.
Very. The study mentions the capital scaling factor of 0.66, which basically means small plants don't benefit from economies of scale. Per unit of output, they are much more expensive to build than a giant centralized facility. It's probably the single biggest financial roadblock.
So the small scale is necessary because of the waste stream, but it makes the project expensive. That makes the sensitivity analysis really important. What are the key factors that could make or break this financially?
The analysis was really clear. 3 things moved the needle the most for both LCOE and LCOR. Number 1 was biomass throughput.
Just process more stuff.
Right, you have to maximize it to fight the lack of scale. Number 2 was the CO2 sale price, and number 3 was the project duration, how long the plant operates.
It's really interesting how critical that CO2 price is, especially for the pure cotton scenario.
It is. The regional analysis showed that for the 100% cotton system, the CO2 sale price had more than double the impact on the electricity cost than the tipping fee you charge to take the waste.
So its main product isn't even electricity.
You could argue its main product is high-quality biogenic CO2. It produces less electricity, but it produces a lot of pure captured carbon. So the price of that carbon becomes its main economic driver.
So this whole study really boils down to a critical choice for anyone looking to invest in this.
A necessary trade-off. It's this. If your project is laser-focused on affordable energy, on a low LCOE, you're going to pick the 50-50 blend because the PET gives you better energy output. But if your project is focused on high-impact climate goals, a low LCOR, you have to prioritize the 100% biogenic streams like pure cotton. You simply cannot have both cheap power and cheap high-efficiency carbon removal from the mixed stream. The purpose dictates the feedstock.
So what does this all mean for you listening to this? We have a viable path here, a way to turn textile waste into something valuable that is, without a doubt, better than a landfill.
But we have to be really honest about how effective it is as a climate solution, and that effectiveness hinges entirely on the feedstock.
The pure cotton delivers that 91% removal efficiency with an LCR of $329 a ton.
And adding the fossil-based PT slashes that efficiency to 59% and more than doubles the cost of the climate benefit to $777, all because you're spending money to capture emissions you just created.
So if the goal is to solve the waste problem and the climate problem at the same time, maximizing that pure biogenic content is, well, it's non-negotiable.
It really is the difference between actually cleaning the atmosphere versus just slowing down the rate at which we're making it dirty.
And that brings us to a final provocative thought for you to consider. The modular approach, this small-scale plant, is really the only practical way to handle waste that's so spread out. But current economics heavily penalize that small scale. So if the goal is truly massive, decentralized carbon drawdown using something like 100% cotton BECCS, does the market itself need to evolve? Does it need to specifically reward this kind of high-efficiency, small-scale removal, even if the electricity that comes out of it is more expensive? I guess we have to ask ourselves, are we willing to pay a premium for a genuine climate solution?